ready to roll.
Yep, your sound is good. So, okay, we're gonna roll on to the 10 o'clock session. This is Dr. Clifton Roozeboom, a friend and my co-founder with PocketLab. And he is the brains behind everything we do. And he has some great demonstrations that he's gonna show you that give you some ideas of tools you can use for distance learning you can use right now. So Cliff, without further introduction, I'm gonna let you go, and I will pop back on. We're a little bit compressed for time, but I'm gonna pop back on about 10:30, 10:35, so we can give people a break, and then we'll continue with the day. If you need the schedule's online at ScIC-conference.com. There's a hashtag on Twitter, ScICCONF. There is Facebook live streaming. There's a Facebook group. We'll post the Facebook group. I encourage all you teachers to join the Facebook group. And there's just ways to interact with the team and a lot of the attendees and participants here. So with that, I'm gonna leave you, Cliff, and I will see you in about 15, 20 minutes.
Great. See you, Dave.
Yeah.
Well, thank you to all the teachers that are here. And like Dave and I believe this is a group of super teachers, and you guys are putting in all this effort to prepare for the coming school year and to learn new things and to, reach your students in whatever kind of learning environment that they might be in. So we just give you a round of applause, and we're here to support you and help you. We're learning this too, and it's tough, and it's not the way any of us want to do it. So I'm going to get started. I am going to talk to you guys today about two subjects, about what is PocketLab, and let me see if I show the right screen, about what is PocketLab, and then go into details about one of my favorite topics, which is temperature and temperature sensors, which I don't know if other people get fired up about it, but I spent a PhD learning about it, so it's near and dear to my heart. So let's start with the basics about what is PocketLab. And we are sort of in the business to bridge the gap between hands-on and digital science learning. We make a variety of things. We make sensors, apps, lesson materials. We do training, professional development, webinars like this, and conferences. And all this, we saw a problem 5 years ago in science where a lot of activities weren't as engaging as we thought they could be and weren't as rich. So we've worked hard in that area, and now hundreds of thousands of students in 60 plus countries use PocketLab in some form for their science learning. So the genesis for PocketLab was this lab setup here on the left. This was my PhD, using all this equipment to measure things like motion and temperature and humidity and chemicals in the air. And this is all the equipment that I needed to do my experiment. Compare that to a PocketLab Voyager, which is in my hand over there, which is here. And we've miniaturized most of that equipment and made it easy for you to go out and explore the world. So simplifying lab equipment is maybe job one. Job two for us is making science more approachable. So on the left, you see this frictionless air track, which is in many high school and university physics classrooms, and it's really great for getting accurate data. But you can do the same experiment with Hot Wheels tracks. And you can see here, we've got second graders colliding cars, learning about physics, and it's the same physics. You get really good results, and it's way more approachable, not to mention, like 100x cheaper than your calibrated instruments. So our goal is to make this more approachable, which in this hybrid or remote learning situation is very valuable. And then the last thing I want to touch on is taking and integrating digital tools in the right places. So we like hands-on, we like doing stuff physically, but there's also times and tools that you need to do things digitally. And so what you see on the screen is our digital lab notebook. And this is an example of how we do science. And this enables things like remote collaboration, having a big repository of resources that you can pull through, and then send to your students. So we want to put digital tools in just the right places, but not all digital, because some stuff is just way better in an analog, hands-on way. Okay, so that's about PocketLab. So let's talk about temperature. And this is a favorite topic of mine because my 2-year-old daughter understands it. She can tell when the oven is on, and she can feel the heat radiating off of it. And yet it's pretty much what I got my PhD in. So first grade definition, working definition is like temperature is how hot or cold something feels, which, you know, is useful and is accurate. A more sort of rigorous definition is this physics definition of temperature is a measurement of how much jiggling or vibrations of molecules in a substance. And it's helpful to think of that in an absolute temperature scale, where absolute 0 or 0 Kelvin is where that vibration or jiggling stops. And then as that substance heats up, you know, this is how we transition through the phases of matter. As those bonds, like the forces between those changes from solid to liquid to gas. And so that's a pretty good definition of temperature, and that'll take us a long way. So I want to poll the audience and ask you a question. What are ways that you know or have used to measure temperature? Put it into the chat. I'll see it scrolling by, and I'll go through some that I know of and that you've encountered. So throw up what you've, thermometers, thermal cameras, probes, fingers, yeah, your sense of touch. All those are great. So let's talk about transduction principles. And transduction means how do we convert something from one form to another. In sensors, it's like this thing that we want to measure to something that's easier for us to measure. So if you look at a meat thermometer that you would put into, you know, your roast and checking the internal temperature, it's a very mechanical device where there's a coil of wire in that probe. And as it heats up, the thermal expansion of that wire causes that a needle to rotate. And that needle rotates on a dial, and that's how we read out the temperature. So you create this, you design this device, you calibrate it with known temperatures, you mark the dial, and that's how you can tell if your roast has hit a safe temperature to eat. Very mechanical. Same thing with mercury and alcohol thermometers, where you have this substance that changes properties, it expands, changes density, in this case, mercury in the ball of the thermometer, and then it moves up this column in this glass tube, and you make markings on that. You calibrate it to known temperatures, and that's how you have a glass thermometer. So very mechanical in nature, which maybe you don't always think about. Okay, so there are also electronic ways to measure temperature, which if you've worked in a lab, you've probably encountered these devices. There's thermocouples, which measure a voltage generated by temperature. There's things called thermistors and RTDs, or resistance thermal detectors, that convert temperature to a change in resistance. There are devices called band gap temperature sensors. These are typically integrated onto computer chips or integrated circuits so that it can measure the temperature of that chip, see if it's overheating, throttle the performance depending on that operating temperature. And then if you've ever used one of these infrared cameras, like from FLIR or night vision goggles, these use something called a bolometer, which is really cool. It absorbs radiation onto a sensor, which changes its resistance. And it can create, you can have arrays of these, so you can have 2D images of temperature, really useful in inspecting equipment or night vision goggles. And you don't have to be in contact to measure temperature. So those are some of the transduction principles on the electronic side. So let's talk about ways that you, the science teacher, can explore temperature, I would say from the basic to like really in depth. And I think we all have know sort of the basics of temperature experiments where you might dissolve salt in water and look at the change in the boiling point or the freezing point. So that's maybe one of the very simple starting point for a physics chemistry experiment. So if you can take those temperature measurements and do it over time, we think it's really powerful because you build understanding of time graphs and interpreting data using a very fundamental foundational concept. So you don't have to struggle with the science component. You can really create graphs that then get into the data analysis component, which we love. Being able to do comparative measurements, so two measurements, comparing a control versus an experiment, or design A versus design B, makes it very powerful along these lines, again, in data analysis and interpretation and how you design an experiment. And then I use it for advanced topics. So I teach a graduate level mechanical engineering course on sensors, and we talk about temperature all the time. And it's really good because everybody understands it, but then you can get into topics about noise and bandwidth and accuracy, precision, filtering, different types of noise, different types of filters. And it's a deep, deep topic, but it goes from first grade understanding on through PhD understanding. So there's some breadth there. So now I'm going to rapid fire through some temperature experiments and try to cram in as many as I can in our time. And what I'm going to use is this device. It's called PocketLab Thermo. It's brand new. I have a prototype here that's hot off the presses. And it is a low-cost, conveniently sized, ruggedized temperature probe with two temperature sensors so that you can do these comparative measurements like we talked about. And it sends data wirelessly so you can record data digitally and see it in action. So PocketLab Thermo is going to be our instrument. And let me switch back. And hopefully you can see my document camera over here. And I'm going to be doing some experiments down here. We're going to try to rapid fire through, we'll see how many we get through. Exothermic and endothermic reactions, insulation, infrared radiation shields, evaporative cooling, and thermos engineering design. We'll do it here. And one note is, temperature changes have a time constant. They don't happen instantaneously. So we might not get to the endpoint on some of these experiments, but we have example data. And all of this will be accessible via link after the conference. So you can go in and play around with this data that we've collected right here. Okay, so we're going to start with a reaction experiment. And so what we have here are two containers. One is road salt, calcium chloride, and baking soda, which I'm going to put some water in here, and it's going to create, it's going to do an exothermic reaction. So really simple. And then I have the classic vinegar and baking soda, which you may or may not have known is an endothermic reaction. So we expect the temperature to increase here and decrease here. And here's my water, or here's my vinegar, here's my water. And I'm going to scroll up here. And we have data from our temperature probes chugging along there. It's gotten hot in my office, so it's like 27 degrees C. The sun's shining in on my big picture window. And I just hit record, and I'm going to place the probes into the cups. And we're going to do this simultaneously. And so it's helpful to do this with room temperature water so you don't get a false change in temperature. But you can see our exothermic reaction increased in temperature and our endothermic reaction decreased in temperature. And you could have guessed the results of this, but I think it's pretty powerful to see this happen together in real time. You can see how it went from this starting room temperature, and then those readings started to diverge. And so we can stop our data recording here, and you can see the data. And on the exothermic reaction, the temperature then decreases as those bubbles evaporate, and the reaction continues. So you get a spike, and then it comes back down to room temperature. Okay, so I'm going to move on from that. Move my chemicals aside. We're going to go on to blubber access insulation. So I'll save that data. I'll draft my probes. And now we're measuring temperature live again. I'm going to equalize these probes, the temperature, by putting them in room temperature water so they can kind of settle in at the same temperature. And now let's talk about insulation. So why are seals and walruses and fat? Because they swim in ice cold water. We have ice cold water here. And they need insulation from those conditions. So I have blubber here in the form of Crisco, which I'm going to coat one of the temperature probes. And I get my hands all oily, touching my computer here in a second. So I'm going to put that onto the probe. It's going to rise in temperature a little bit because of my hands. But then let me start recording. I'm going to put it into cold water, and we can look at the change. And our blue probe will start to cool off, but the red probe cools off much, much faster. And this is because of two effects. There's the insulation from the blubber, the Crisco, which is increasing the temperature gradient between the temperature probe and the water, or sorry, increasing the distance, which decreases the temperature gradient. And so that's one effect. And also, there's a lot of thermal mass. We've added a lot of mass to the temperature probe. So that creates some inertia, some thermal inertia in our system. So changes will happen more slowly. And this happens in both directions. So I take it out of my ice cold water, put it into some room temperature water. And you can see my uninsulated probe changes almost like back up to temperature within, like 10 seconds. And my insulated probe is lagging behind. So, there's our experimental data. Insulation works both ways, like cool to hot, hot to cold. Okay, rapid fire. Save that trial, and then we're on to infrared radiation heat shield. Okay, so I gotta take off my blubber, rearrange my station. Okay, and then I have here a heat lamp, which was a little hard to find. It's hard to find incandescent bulbs these days. I had to scour all over the place. But there are three main methods of heat transfer. That is convection, conduction, and radiation. And radiation becomes important significant when substances are glowing. Like when an incandescent bulb, the radiation, you can see the radiation coming off of the filament. So we're going to put these two probes, which, their temperature is still kind of changing because there's coming out of that water. And we're going to record some data. And then I'm going to turn on the heat lamp. And you can see those temperatures start to increase very quickly. And these probes are black in color. So they pretty much act like black bodies. So they're very absorbent to radiation. So I have here a piece of glass, which you can see is very transparent to visible light, visible radiation, but is pretty blocking to infrared radiation. So if I were to take it and I were to put it in front of the blue probe, and I'm going to leave the red probe exposed, you can see the slope of the increase in temperature starts to fall off for the blue probe versus the red probe. And this one is one experiment where we won't really be able to get to a steady state in the time that we have, but we can stop and check out the data that we do see. And at that, right about here at this time point, if you can see on the screen right here is when I put the shield in front of the blue probe, and you can see how that temperature, the slope of it starts to change. and not increase as quickly. So we'll save that data. Now here's live data. The red probe is significantly hotter than the blue probe, about 2.5 degrees C. Okay, so we're cruising along. Next, we are on to, let me see my agenda. Oh, evaporative cooling. So I'm going to use the same setup, and now I'm going to bring in a fan. Oh, scrolled too far. Sorry, my computer's a little laggy with everything going on AV-wise. Okay, so if you can see here, I have a tabletop fan. I have 2 temperature probes. I'm going to start to turn. I'm going to turn on that fan. We're going to blow room temperature air over those temperature probes, and they're going to cool off some, but actually they're going to just come to room temperature. Like turning on a fan doesn't change the temperature of the air. That's not why you feel cooler in front of the fan. It helps with, heat transfer, this convective heat transfer. And then if there's any moisture on your skin or you're sweating, it also helps evaporate that moisture. So we have here is a little paper towel that is dipped in water, and we'll put this over one of the probes, and then you will start to see that probe cool off much, much faster. This is because of that evaporative cooling, which absorbs heat energy, which is transferred from the probe into the jacket of water around the probe. So this is also this kind of setup, it's called measuring a wet bulb temperature for all you weather geeks out there. Wet bulb temperature is used to measure things like dew point. It's also a way for you to measure humidity. And this is kind of somewhat similar to a setup that you would use to measure wet bulb temperature. So after, less than 2 minutes, you can see how the temperature for both of these sensors was starting to come back down to room temperature, but you put that jacket on there and it starts to fall much, much faster. Okay. We are cruising along. So I'm going to save that. And I did our reactions. I did methods of heat transfer. Oh, okay. And I wanted to do one example of a engineering activity, and this one is takes much too much time. But here in the photo is an example of a thermos engineering design competition we had in our office between groups of interns. And I saved one of the designs, and this was, we used temperature probe to measure the temperature of what we called a vaccine that we needed to refrigerate during shipping. So we had some design requirements over how that was to perform. And this was one of our interns' designs. He went kind of crazy with the tin foil. And you can see on the screen, there was another design, so design A and design B. And it's a little bit small, but here was the time graph of the temperature readings. Blue was one design, red was the other. The red performed better in terms of refrigerating the vaccine. And then this yellow kind of squiggly line was the room temperature. And here, after a few hours, it got hot. That was when the sun was shining in through the window. And you can see the jogging up and down. That's the AC system turning on and off, cycling on and off. And all those temperatures sort of start to converge after this was a 17-hour test. So there are so many things that you can do with a temperature probe. And there are even more things you can do if you have 2 temperature probes. So PocketLab Thermo, we just launched it. It's available on our website for pre-order. There's a special exclusive deal for all ScIC folks to get it. It's $39, and you can use the promo code ScIC3 when you're ordering it. And we already have about 24 lessons for it. This is an example of how you can use it, both either in person or remotely. But you know, temperature is a powerful thing. It's a good introduction into science, but it goes deep. I mean, I have lots of grad students that struggle with concepts that we pull out from measuring temperature and doing temperature experiments. So you should try it out. All right, I think that's all my time.
Hey, Cliff, can you hear me?
Yeah.
Back on here. Great, great. Thanks. Thank you very much. Hey, so we do want to do a break, but I do want to just a couple quick questions. And I know you can do these super quick. It's Bluetooth, right? It's completely wireless Bluetooth.
Yeah.
Couple
Works
people
like a
asked
Bluetooth mouse. You can be about 50 feet from it, so you can put it in your fridge and then set it up at your desktop computer and see if anybody's making a run on midnight snacks.
Yeah, exactly. And then a couple of people asked what graphing software. So it's not actually graphing software. It's part of that that's in the PocketLab notebook, right?
Right. Yeah. So everything was an example of using PocketLab Notebook, which you can go to the PocketLab.com/app and try out. We'll send a link to this exact lab report that we did, but you can create a login and play around with it. So yeah, PocketLab.com/app.
And there is a free version that you can use.
Yeah, and it's compatible with everything: Chromebooks, computers, even your phone, whatever.
Yeah. Okay. And then there's a licensed version if you have a classroom and everything, you know, and you want to have students on and set up your classroom.
Yeah. If you want to have students and pull like lessons and then push those out to your students through remote learning, there's ways that you can do that through our Pro software.
iPad. I saw somebody ask iPad. That's no problem.
Yeah. Yep. We support it all. Linux, for all the Linux users out there, we got you.
Great. And one last question. I saw a few people ask, do we have donors choose? And yes, we work with NASCO, basically, on donors choose.
Yeah. And
I'll point out that if you start a donors choose project, send us a message. We do a 10% matching of that. So if we know about it, it's hard for us to know when a new project comes up. You post your project, send us a message, and we'll be one of the first people to donate. We'll put 10% to the project. Great. I see a ton of, there's still a ton of comments. We'll answer the comments in chat. I want to give you guys a break. I know you've been here for a couple hours now. Thank you without a break. So we have about a 5-minute break. And right on after this, we have Jason Lindsay from Hooked on Science, and I see him getting set up. So Cliff, thanks. That was fantastic, and I really appreciate it. Thanks for making ScIC a great event for the teachers.
Thanks all you super teachers. We appreciate you.
Okay, great. I'm going to go to the break now.